now? Okay. All right. We'll just dive right into it. Okay. All right. Well, one of the things that we've been seeing, or one of the things that we've been working with for the past couple of weeks is the idea that you can have a population, and that population can be roughly normally distributed or perfectly normally distributed for that matter. And then you can also take samples from that population. And if you take the sample means of repeated samples that you take all over and over again, if you sample that population over and over again, those sample means themselves, if you plot them on a distribution, they are also normally distributed. Well, the nice thing about that is two things. Number one, the original population, if you take big enough sample, the original population doesn't have to be normally distributed. The sample distributions will often be much more normally distributed than the original population is. So we get a little bit of a leeway when we're dealing with populations that are not really perfectly normally distributed. In addition to that, the sample means are spread out much less than the populations are. So we get a chance when we work with a sample to work with values that we can rely on a little bit more to be closer to the population mean, especially as the sample gets bigger and more robust. And we know all of those special dynamics that work for the sample population in terms of standard deviations also work for the sample distributions, except that we use a modified version of the standard deviation called a standard error. Anybody remember what this whole thing is called? The idea that we can take these samples that are normally distributed and have all these properties. Central limit theorem, exactly. All it is kind of summarized in the central limit theorem. Okay, and basically in order to use central limit theorem, we have some assumptions. The main primary assumptions are that the original population is roughly normally distributed. It doesn't have to be perfect, and that especially as the sample size gets bigger, and that the sample that we're taking is randomly selected. In other words, it's not a biased sample or something like that. Okay, so let's take a look at a normal distribution. This is an example of a normal distribution. I'm going to make up a reason for it. Let's say it's IQ. It isn't really an IQ distribution, but it starts, the average is 100, so let's call it that. Okay, in this population, notice I say mu, Greek letter, because it's a population mean. Sigma for the standard deviation is 20. And if I draw it as a distribution, we know that between two standard deviations below the mean, say 60, and two standard deviations above the mean, say 140, we have 95% of the population that's in this distribution. If I go to three standard deviations above and below, I have 99.7%, roughly. We know really for 95 it's 1.96 plus and minus, because we know that idea of using 2 for standard deviation for 95% is basically an estimate. Okay, so now what does that tell me? That tells me I know certain things about this population. Like for instance, I know that 2.5% of this population has an IQ over 140. And how do I know that? Well, I know between 140 and 60 is 95%, so that leaves a tail here, and it leaves a tail down here, and I know that leaves that's got to account for 5% of the population. So since this is symmetrical, because it's a normal distribution, it's got to be 2.5% here. So 2.5% of the population is above that value. Oops. Put that in there, see if this will work for me. Okay. Okay, so now, here's our sample distribution. We take an infinite number of samples from that population of size 16, and we find the mean of each one of those samples of size 15, and we replot this distribution. Well, now, the mean, we're going to call that x bar. Let's say we get lucky and it's 100. Well, if I took enough of them, it's going to be 100. X bar is 100. The sample distribution, sample standard distribution, or standard error, as we're going to call it now, is equal to 5. How do we get that? The population standard deviation was 20. The sample size is 16, so it's a standard deviation 20 divided by the square root of the sample size 16, which is 4, so 4 into 20, is a standard error of 5. So now we know that if we take a sample from this population, half the time it's going to be above 100, right? Half the time it's going to be below 100, right? And 95% of the time the sample is going to be between 90 and 110. 2.5% of the time it's going to be above 110. So now, if I take this sample now, if I take a sample of this, and I tell you that we take a sample of 16 people from another population, we don't really know if it's different from this population, or if there are differences, or if it's really the same population. We take a sample of 16 people. We find that the average for those 16 people is 110. Okay? How often would we get that result of 110 if we took a sample of 16 people from this population? Well, that would occur 2.5% of the time. We'd get 110 or higher. So it's conceivable. It's not going to happen that often, but it's conceivable that that could happen. Okay. How about 115? How often would that happen? Anybody want to hazard a guess? Right? It's 3 standard deviations, right? Between here and here is, say, 99.5%, 99.7%, almost 99.8%. That's only 0.1%, right? We're only going to get a value of 115 for an average 16 people, 0.1% at a time, 1 out of 1,000 times. Right? Yeah, 1 out of 1,000 times. Okay, so that's not going to come up very frequently, right? Can I say for certain, if I get an average for this group over here, 115, can I say for certain that it's a different population mean than for this group? I can't say for certain, right? Because, you know, there is a possibility that that could happen. Well, how about for 120? That's even less, right? That's even a very tiny percentage. But can I say it can't happen? No, because this is asymptotic. It never really reaches this line. You guys read about the Higgs boson that they presumably feel that they've discovered, right? Now, if we're talking 3 standard deviations, we're talking 0.1% probability of that occurring. We're talking 4 standard deviations. We're talking 0.00001. If I were to go all the way out here to 155, that would be, how many standard deviations would that be? That would be from 100, that's 11 standard deviations, right? I mean, that's like super infinitesimally unlikely that that would ever occur, but it's not impossible. When they talk in physics about proving that this particle that they discovered is different than all the other ones that they know, you may have read in the paper that that they were not willing to accept the fact that they really discovered it until the probability that they would have another particle that's already known that would behave exactly that way is 6 standard deviations difference from chance. Okay, so in other words, they would only do that if it were like infinitesimally likely that it could be some other particle. Okay, and they have to do it that way because they're dealing with a lot of particles, a lot of interactions, and millions of collisions and stuff like that. So they got their reasons for doing that. But 6, you can see, when you say 6 standard deviations probability that it's a different particle, they want to really be sure. Somebody in the other class told me that like they got tired of waiting to get enough data, so they did it. They announced it at 5 standard deviations. But in any case, that's really unlikely that they're wrong, right? So now, we can't afford that though, right? If we were going to do that, we'd have to, you know, if I wanted to compare the blood pressure of Americans to Frenchmen, and we wanted 6 standard deviations, we'd have to, you know, sample hundreds of thousands of Frenchmen, hundreds of thousands of Americans. It would be unwieldy. Typically, what probability are we willing to accept in public health when we do a study that 2 populations are different, that a drug is better than a control, that an intervention means fewer cases of asthma than not doing the intervention? Anybody hazard a guess? What's that? 2 standard deviations, right? 1.96 or 2 standard. And what's that probability of? What's the probability of being wrong when we are willing to accept it at only 2 standard deviations? 5%. There's 5% chance of being wrong. We've got 1 in 20 chance of being wrong when we do most of these studies, if we're willing to accept that level of error. Why are we willing to accept that level of error? Because on a practical basis, in order to do these studies, we can't afford to have enormous sample sizes in many of them, right? Sometimes you'll go a little further and you go to, you know, like 99% confidence or probability of being wrong, or 1%. What's that 1% called, or the 5% called? What kind of error is that? Type 1, type 2, what's the other name for it? Alpha error, right? Alpha is when you say they're different. Alpha error is when you say they're different and you're wrong. Beta error is when you fail to say that they're different and indeed they are. Alpha error is usually considered worse because you're saying, for instance, that a drug works better than the control, so now you're going to give it to 1 million people, right? So that's kind of a bad thing. Beta error, if you come close and you don't have enough evidence to say that that it's really the same, but that if the drug does work and you don't quite have enough data, you know, you only have 6%, you have a 6% chance of being wrong or 9% chance of being wrong, you have a chance to redo the study and re-examine it. Many years ago, when I was in college, there was a group that did an experiment with planaria. Anybody know what planaria are? They're popular. They used to be popular in pet shops to feed, you know, pet fish and stuff like that. They're flatworms. They're skinny little flatworms. These guys did a study where they used light to attract planaria, so that they would put them in mazes where only left turns or right turns or something like that, and they would train the planaria to turn constantly through a maze to reach food. And they'd have to run the planaria through the maze, I don't know, a dozen times or something like that. And eventually they could prove that, like, the planaria when you put them in there, eventually they were able to navigate the maze in less time than they were before when you started. So basically you say that they learned something, right? What they did then was they took the planaria and they ground them up to put them in a blender, right? Made planaria goo. And they fed it to other planaria. They also fed planaria that were ground up that had not been trained to another group of planaria. When they did that, don't laugh at that, this is true. When they did when they finally did their study and they tested the planaria that had been fed but never gone through the maze, they found in their study, with less than 5% chance of being wrong, that the planaria that ate the smart planaria performed better in the maze than the planaria that ate the naive, I don't know a better word for it, but naive planaria, right? So, does this make any sense to anybody? It does? No, it doesn't make any sense. It seems like, gee, it would be nice if that would work, because then we could eat, you know, instead of learning biostatistics, we could go home and eat it, right? But they couldn't get a legitimate journal to publish it. They started their own magazine called the Worm Runner's Digest. It was around for about, I don't know, 5 years or something like that. And they published basically every kind of like weird study that anybody, you know, all these paranormal studies and all this kind of stuff. But what do you think happened when somebody tried to replicate their results? Didn't work, right? They got lucky. Either they got lucky or they got careless, who knows what. But lucky is good enough, because you know, as we've learned, 1 out of 20 times you're gonna, even though there's no difference between the planaria, 1 out of 20 times you're gonna get enough evidence to say that they're different, right? If you do the study carefully. So typically what happens is we want to avoid that. And the way that's usually avoided, if that does go wrong, is that we in addition to knowing that it's less than 5% probability, we're interested in exactly what the probability is, and we're going to talk about how to figure that out. But we're also, what will also happen is that most studies get replicated. They get checked by somebody else, tries to do it as well. Right? A lot of things this has happened with, you hear about studies that show cancer in mice, you know, when exposed to a very large level of a certain a food substance or coloring or saccharin or whatever, and then they can't replicate this. There was a big Canadian study that studied, was it saccharin, I guess it was, something like that, and then nobody could replicate their results. So that's still kind of an open field. Okay, so we're going to use this to try and demonstrate differences. That's really what we're interested in, is differences. Is this group different than this other group? Is the drug performing better? So these guys, their health is better than the guys that took the control instead of the drug. If I do this intervention, if I educate people about how to avoid asthma, are their kids going to have fewer emergency room appointments than emergency room visits than parents who are not trained, and so on and so forth. So these are the things that we're going to want to do, and we need to find a way systematically to test these theories, or what we're going to call hypotheses. Okay, so first thing is assumptions. The variable is quantitative. We don't do this with hair color or whatever, and so on and so forth. It could be proportions. It could be scalar numbers. The data is the selection. Your sampling is random, and the population distribution that you're taking the data from is roughly normally distributed. That's less and less important when you deal with a larger sample because of this the central limit theorem. Okay. And the way we do this is we construct a hypothesis. Mean 1 is equal to mean 2. Mean of the group that took the drug is equal to mean of the group that didn't take the drug. That's called our null hypothesis. We play devil's advocate. We say, when we want to prove there's a difference, we start off by saying there's no difference. Okay? The mean of group 1 is equal to the mean of group 2. Or, if we know the mean of a population, the mean of the sample that we take from another population is different from that population mean. Okay, we want to prove that, that's the way we start. We want to prove that they're different. So we propose also an alternative hypothesis. And you can have 3 kinds. The one that we use most of the time is called a two-sided hypothesis. In other words, mean 1 is equal to mean 2 is our null hypothesis. Alternative is mean 1 is different from mean 2, does not equal mean 2. That means we don't care if it's bigger or smaller, just that it's different. We'll worry about bigger or smaller when we get the results. What that means is that you have to be 2 standard deviations apart in those means when you compare the 2 groups, because you got to be 2.5% on past 2.5% on this side, past 2.5% on that side. You could also have a single-sided alternative hypothesis. Mean 1, null hypothesis, mean 1 is equal to mean 2. Alternative hypothesis, mean 1 is greater than mean 2. In other words, we're assuming it's only bigger. That means you can have all 5% on one side, which means you don't need 2 standard deviations. You can get away with, I don't know, I guess roughly 1.7 standard deviations. It's less rigorous. For the most part, because it's less rigorous, we almost always do 2 tests, two-sided tests exclusively, because a lot of times we're not really sure what the difference is going to be. Occasionally, I guess if you're doing a certain kind of drug test where, for instance, you're testing whether a drug reduces blood pressure, and you know that the way it works, it's a vasodilator, and you say vasodilator, the only thing it could possibly do is lower blood pressure. So we're just concerned whether or not it's really effective at lowering blood pressure or not. It can't raise blood pressure, so you might do a one-tail test in there because there might be a physical constraint that could make it not go the other way. Okay, but most of the time we're doing 2-sided tests. But we would, and this is the way we would propose them: greater than, less than, or not equal to. We use the 2-sided one most frequently. Okay, and how do we do this? We need to know how many standard deviations these things are apart. How do we do that? How did I just do it now? I said 100, mean of the population, minus 115, the mean of the sample that I have, one mean minus the other, and then we put it over the standard error to see how many z-scores apart they are. In this case, we wrote t, right? X bar minus the mean, before it was 115 minus 100, over the standard deviation of the population divided by the square root of n. There's a t in front of that, right? If we know the population standard deviation, we put a z over there. The other reason we would put a z over there is why? Instead of a t. If we have a big sample. If we have a very large sample size, we can also use t, even if we're getting the standard deviation from our sample and we don't know the real population standard deviation. Okay? If we know the population standard, we could put a z here if we know the population standard deviation, or if our sample size is very big. technically, a lot of statisticians use big, bigger than 30, they consider big for a few reasons. Okay, you could be more rigorous if you wanted to, but you could get away with using the z-score in most situations if the sample size is bigger than 30. Okay, so this is the formula that's going to give us a number of z-scores, or number of standard deviations, two means or apart. We do the same thing with proportions, right? Let's say we have a population which has a 10% rate of diabetes. And we know that's the population proportion that was measured in the big study. Now we get a new population, maybe an older group, younger group, maybe a group from another state, right? And we discover that instead of 10%, we get a sample of 100 of them, and it turns out 12 of them have diabetes out of 100. Their proportion is 12%. The one that we're comparing it to is 10%. But if we take 100 people, it's very easy in this population, which is 10%, to get 12 out of 100, right? Even though we know it's in reality, it's 10% for the whole population. Very easy to get that little bit of a difference. So in order to figure out what the probability is that these guys over here, their 12% is really different than that 10%, that 0.12 is really different, is we have to figure out how many z-scores apart they are. How do we do that again? Same as before. Difference between the 2 point estimates. Before it was means, now it's proportions. 0.12 minus 0.10 is 0.02 over the standard error. How do we calculate standard error with proportions? It's the probability for the population times 1 minus the probability of population divided by n, and we take the square root of that. Right? That gives us our proportion. If you don't know the population proportion, or you don't trust this calculation, what number could you plug in there? What's the biggest number you could put in here to get what would make this the biggest number? Okay, and the most conservative number. Well, let's see. If this is 0.1 times the sample size is set. This is 0.1 times 0.9, what do we get? We get 0.09. If this is 0.2 times 0.8, that's 0.16, right? It's getting bigger. 0.3 times 0.7, 0.21, right? 0.5 times 0.5, that's 0.25. That's the biggest number you're ever going to get. So you can always, if you have no data at all, put in 0.5 for the probability and use that as a standard error. That's the most conservative standard error that you can get. Okay, you can't get a bigger number than that. Okay, so we just figure out what the z-score is. If the z-score is less than 1.96, what do we say? We keep the null hypothesis, they're the same, or we say they're different if the z-score is less than 1.96. It's inside of that range, right? So it's perfectly possible we could get a sample that size when both populations are the same, right? We only say that they're different, reject the null hypothesis, when we're outside of that range of 2 standard deviations or 1.96 on either side. Okay, or whatever the t-score happens to be, whatever, based on the sample size. This is always going to be z, because one of our assumptions when we work with these proportions is how many subjects do we have to have in that group? Anybody remember? 30 total, right? 30 total, but you need at least 15 in this group and 15 in this group. In other words, it's cheating to have 10 here and 20 here. So you know you have at least 30. What did I just say about the z-score? Even if we don't know the standard deviation of the population, if the sample size is bigger than 30, right, we can just use the z-score instead. So we can justify using the z-score because our primary assumption is we can't do this whole thing unless each group has 15 subjects in it, a minimum of 15 subjects in it. Okay? Right, so that'll work for us. Okay, next thing is the p-value. Now, not only can I tell, based on the number of standard deviations apart these two values are, whether or not I can reject the null hypothesis and say with less than 5% chance of being wrong that the two populations have different means, but I can also be more specific. I can say if the z-score is 2.58, that sticks in my head. That's 99. That's a 99% confidence interval, right? 0.5% here. I could say that if the z-score is 2.58 or minus 2.58, that the probability of them being from different populations, that's really, of being from the same population, that's really 0.5%, right, for a two-sided test, because it's so far out. So for any z-score, I can actually look up what the area in the tail is, and that would be the probability that I would be wrong if I say the two groups are different, right? So, and we would only reject the null hypothesis if the probability is less than 5%. But we can always calculate the actual p-value, the actual probability that way. Okay. Just so that we, if we have two different distributions, and let's say our sample comes up here, right? That sample could be from either one of these populations, right? It could occur this percentage of the time if we were looking for this population, and it could occur this percentage of the time for this population, right? So now they are two different populations. So the probability, I would need to be at least out here in order to say that this would have to be at least as small as 2.5% if I were using a two-tailed test for me to reject the null hypothesis. This area in here represents the alpha error, the probability I'm wrong if I reject the null hypothesis. This area from here down represents the fact that we can't get it from this sample over here, but that represents the beta error. Chances are that we would fail to reject the null hypothesis when indeed they really are different. The alpha errors usually, as I said, considered worse than beta errors, because the beta error is when they are different, but let's say your z-score comes out to be 1.9, not 1.96. So the probability of being wrong is maybe 6.5%. And you say, I failed to reject the null hypothesis because I didn't get below 5% chance of being wrong. Even if they're two different, those two different populations with two different means, you really should have rejected it, but you failed to reject it. That's called a beta error, right? Again, not as bad because you can always go back and redo the study with a larger sample size and so on and so forth. This area in here, which is the difference between the beta error and 1, is called the power. I wouldn't worry about this right now. We're going to go over that a bit more as we go on. So don't sweat that part. We'll get to that last diagram again when we start talking about sample size and a whole bunch of other things. Okay, so why don't you guys open up homework 6 and 7. They're available both in the class session and in the assignment section, both. So you can open it from the class session if you want. It might be easier to get to. Okay, and I'll give you guys a chance to catch up. I'm going to start with homework 6. Oh, not that one. Okay, I'm going to get started. So you can continue to open up. Try and pay a little bit of attention to me in the background here. Okay, Time magazine quoted a poll performed in 2002 of 100 Americans in which only 4% said that they were vegetarians. I mentioned before in the other class that nowadays I don't even know what that means, right? They have 9,000 different kind of vegetarians now, right? So, but let's say they maybe you can let them make that judgment if they answered yes or no to that. Only 4% at that time, probably higher now, right? Said that they were vegetarian. This is a sample of 1,000 Americans. Does that mean that the entire population of the United States, that they're 4% vegetarians? No, right? We don't know that yet. We don't know what that is. In fact, we'll never know that. But what we can know is we can know a range based on this sample that we're 95% certain will capture the real percentage of vegetarians in the population. Okay, so Using Excel, I'm going to do it on the board for now, but I'm encouraging you to use Excel as you go through these exercises. And when we do it online, I'm going to be using Excel. It's a little bit harder for me because the keyboard, wireless keyboard and stuff is difficult to work with. But we're going to examine what the 95% confidence interval for the true population proportion of vegetarians are in that year in the United States. Okay, so P cap, right? We use P cap to represent our proportion for our sample is 0.04. Okay, so now that's a sample of 1,000 people. We know we suspect that this is normally distributed. If we took another sample of 1,000 people, another sample of 1,000, another sample of 1,000 people, we get some of them higher than 4%, some of them lower than 4%. Sample size that we used here is equal to 1,000. Okay, so now, what do I need to know here? Remember that formula we had before? Z is equal to, what was it again? P cap minus P over the standard deviation and so on and so forth. Well, right now I'm really interested in the confidence interval. So I'm going to use kind of a form of that, which says that, let's see, 95% confidence interval is equal to P cap, right, my point estimate or my average, plus or minus, well, let me think here, plus or minus the z-score for 95%, right? Instead of z is equal to, I'm looking at a z-score, what's going to give me 2 standard deviations below this point estimate and 2 standard deviations above this point estimate, times the standard error. Okay, how do I calculate my standard error? My standard error is going to be equal to the square root of 0.04 times 0.96 over sample size, which is 1,000. Okay, so what's my standard error equal to? Okay, if you got Excel, that should be pretty easy to do. I got my phone, so well, you guys are working on it there. I'll work on my phone.
Where did you get the 0.96?
It's P times 1 minus P,
Okay.
right? 1 minus 0.04 is 0.96. Good question. I get 0.036 for the top, 0.0376 for the top of that, divided by 1,000 is 0.000376, and I'm going to take the square root of that, and I get square root of 0.006. I'm going to round it off. 0.006 is what that resolves out to. Okay, hopefully you guys got the same thing. Okay, so my 95% confidence interval is equal to 0.04 plus or minus z times 0.006. What's z going to be for a 95% confidence interval? 95? What? 1.96, right? If it were 99% confidence, what would z be equal to? You remember? 2.58, right? What's that? Oh yeah, absolutely. You can use the z. You can use your Excel. You can look in the table. This is not something you have to memorize, but it just happens that after a while you start use 95%, 90, 95, 98%, 99% confidence intervals come up so often that eventually you start to learn them. 90 is 1.64. Okay. All right, so this is going to be 1.96. I'm, for argument's sake, going to call it 2 for the moment because I don't have Excel in front of me and I don't want to keep poking on my phone. So it's going to be equal to 0.04 plus or minus 2 times 0.06 is 0.012. So that's going to be equal to 0.028 to 0.056. So the 95% confidence interval is 2.8% to 5.6%. Okay, so we did this study of 1,000 people that we surveyed in the United States. And based on that survey, we got a rate of 4%. But we don't really know how accurate that is. Instead, we calculated a confidence interval. Now we can quantify this, right? We can say that the true population mean for population proportion for vegetarians in the United States in that year, 12 years ago, whenever that was, right, is between 2.8% and 5.6%. How sure am I? I'm 95% sure. Before, I had a nice firm number, like 4%, but I had no idea how certain I was. Now I have a range, but I can quantify the level of certainty that I have. Okay, get the idea? Okay, so now if I go to another country and they tell me, oh, Tony, you know, we did an exhaustive study, we measured everybody in the country, and we found that in India, for instance, that there are 7% of the population of vegetarians. Can I say with 95% certainty that it's different than the United States? Yes, I can, because I know the United States is in this range somewhere with 95%. So if India is over here, I know with 95% certainty it's different. If India were 5.7%, well, you know, 5.5%, I couldn't tell for sure it's different from the United States, because that, you know, my 95% confidence interval includes 5.5. So this helps us determine whether or not we can say with 95% certainty, with less than 5% chance of being wrong, whether or not two things are different, two groups are different with a proportion. Okay? We do it with a proportion, we can also do it with numeric variables, a scalar variable. Let's do it now. Oops, gotta put that down. I'm gonna close the ink layer. Okay, and let's go to another example. Okay, you'll have plenty of time to play with this. Okay, this one involves it gives you numbers, and you actually have to find your own standard deviation. You can use Excel or you can use SPSS. I'll go over both of those when we do the, here's a good one, when we do the online session. This is, they sampled the starting salaries for 81 psychologists in 2003, and they found that the mean income for these sample of 81 randomly chosen psychologists that just got a master's degree, mean income was $43,500 with a standard deviation of 16,870. Let's construct a 95% confidence interval for that. Okay, so this time we're talking about a mean, right? So we're talking about X bar plus or minus, well, let me see. Now the z-score, do I use a z-score or a t-score here? Standard deviation of the, not of the population, but of the sample, right? Can I use a t, I should use a t-score, right? But my sample size is 81, so I can get away with using a z-score. If I wanted to, I could pull the t-table up, and I would go to how many degrees of freedom? 80 degrees of freedom. I would go down to the row with 80 degrees of freedom, go across to the t-value for 95% confidence interval, or 5% alpha, and I would get that t-value. It might be something like 2.03 or something like that. I could actually do that if I wanted to be more accurate. Well, but for this purpose, since we have such a big sample, I'm going to say, okay, I'm going to use 1.96. Plus or minus 1.96 z-score times the standard error. What's the standard error here going to be? Okay, standard error is going to be the standard deviation, 16,870, over the square root of the sample size, which is 9. And what does that come out to? Oops, excuse me, square root of 81, which is 9. So it's 9 into 16,870. Anybody got that? I'm going to be able to do it in my head faster than that. You have all the advantages over me here. 9 is 1. 778 is 1871? 1874. Okay. 1874, standard error. Plus or minus 1.96 times 1874. Okay? Or roughly 2 times 1874. Right? So, x is 43,500 plus or minus 2 times 18, that's about 3,600. I'm going to call it 3,500. I'm just going to round it off to 3,500. You know that, you got to actually do the math here and stuff, So I'm going to round it off to 3,500, make it easy for myself. So it's 40, plus or minus 3,500. Well, that's 43,500. So the lower number when I subtract it is going to be 43,000. And the bigger number when I add it is going to be 40,000. And the bigger number is going to be 47,000. So based on this sample, I'm 95% certain that the true mean starting salary for psychologists in the United States, not just these 81, but the United States, is between 40,000 and 47,000. Okay, the true mean. Okay, before I had 1 point, 43,500, but I don't know how accurate that point is. I can't quantify that. Now I have a way to describe how certain I am of that result. If it were a bigger sample, that'd be narrower, right? If I were willing to be less confident, that'd be narrower. If I wanted to be more confident that I actually captured it, I'd have to make it a wider range, right? 99% confidence would be at 2.58, so the range would be what? Be like 46 to 48 or something like that. Okay, so everybody could do this, right? Okay, this is probably before you took this course. Has anyone done this in the last 5 years? One of us. Okay, but now all of us can do it, right? Right. So you got a couple of other. You're going to do these for homework. You got a few more examples like this. Some of them are proportions. Some of them are numeric variables. In any case, some of them will give you the actual numbers and standard deviation. Some of them just give you a list. If they give you a list, you have to use Excel to calculate the mean yourself, calculate the standard deviation yourself, the standard error, and so on and so forth. But you're doing exactly the same thing. It's just that you have to take those extra steps to figure that out for yourself. Okay, let's take a look at homework 7 where we get into hypothesis testing now, which is the meat of what you did. You started with, again, this is similar to what you just did tonight. Okay. Okay, homework number 7. Oh, let's make this go away. Oh, I gotta put this down. Didn't go away. Good, there it goes. Okay. Wonder if that's a good one to start out with. Okay, let's start. This is an interesting one. New York City mayor election is heating up. Christine Quinn is the early front runner. I don't want to start with that one. I want to start with a numeric one, a little easier to understand. Okay, here's one. Okay, some guy sells Marc Jacobs bag. I've made the price up on this. They're probably way more than $400, right? Okay, so this store sells Marc Jacobs bags, and they want to know, they think that their mean sales per purse is $400. They want to know if it's more than that. They took a random sample of 100 customers, and they found the average sale for each of those randomly sampled 100 customers was $420 with a standard deviation of $40. Well, do we know really if maybe their sales, maybe they do thousands of sales per week. Do we really know, maybe it's an online store or something like that, do we really know, based on these 100 customers being 420, if their average sale is really over 400? We don't know that, right? Right? We know that those particular 100, the average was over 400, but that could just be chance came up with a higher number. Even if in any case, if we took 100 customers and it was an average of 400, well then what would happen is half the time we didn't get a number below 400, half the time we'd get a number above 400. We'd hardly ever get exactly 400. So we don't know what to make of that 420, whether or not it really indicates that they're getting more money, their whole customer base is really more than 400. Okay, so we have to figure out how many standard deviations difference is there between their proposed mean for the population of 400 and our sample mean of 420. You guys remember how we do that? We took our we calculated a z-score, right? That z-score is equal to, what's it equal to? It's equal to x bar minus the mean over the standard error. Okay, we need to calculate that because we need to know what that z-score is. If that z-score is bigger than 1.96, that means we can reject the null hypothesis, say that, oh, they're making it really is different than 400, whatever it is, whether it's less or more. Okay, so I should really formalize this though. How are we going to formalize this and describe what we're really doing here? Well, we're going to set up a hypothesis. The hypothesis is we're going to play devil's advocate, as I said before. There's no difference between what the sample determined and what the mean that they thought they were getting. In other words, the mean that they calculated is the mean that we're working with. What is that called again? I'll call that 2. What is that called? What kind of hypothesis? Null hypothesis, right? What's our alternative hypothesis? We could play around with one-sided and stuff like that if we want. Let's not do that now. Let's say just not equal to. They're different, right? So we want to prove with 95% certainty, less than 5% chance of being wrong, that we can reject this and accept this instead. Okay, and in order to do that, what z-score do we have to have? How many standard deviations between the two means that we have to have to be 95% certain, less than 5%? We need 2 standard deviations. Actually, technically, because it's a big sample, 100, technically, we need 1.96 standard deviations. Okay, let's do that. The z-score is equal to 420 minus 400 over the standard error. What's the standard error? The standard error is equal to the standard deviation 40 divided by the square root of the sample size 100. That's equal to 10 divided by 40 is 4. Okay, the z-score is 4, that's 20, 4. That's 20 over 4. That's 5. That's 5 standard deviations apart, right? What's the probability of getting 2 means that are 5 standard deviations apart? It's very, very tiny, right? Had this been, so we can reject the null hypothesis. Okay, make believe that this had been 1.97. Can I reject the null hypothesis? Yes? Why? Because it's bigger than 1.96, right? It's bigger than what I need for the 5%. How about if this had been 1.89? No, I couldn't because I would be too far in and I would have more than a 2.5% chance and 2.5% chance on the other end. So I have more than a 5% chance of being wrong if I reject the null hypothesis, right? So I need that to be big enough for me to reject the null hypothesis. Okay, so I could do this again, except this time I might try doing it with a proportion. Let's go back to Christine Quinn. I think this is going to be a really interesting election this year. Okay, New York Mayor, Christine Quinn is an early front runner. This is all fake data. A random sample of 400 voters found that 230 were likely to vote for Quinn. What's the proportion there? Oops. What's the proportion for Quinn? Let me try red. P cap for Quinn is equal to 230 over 400. What's that proportion? What is it? 40 into 23.
0.6.
Point what?
6.
I'm sorry?
0.6.
0.6? 0.60. Okay, she got 60% of that 400 votes. Okay, so now we want to know if the election were held today, does that indicate that she has the majority of all the votes in New York City? Randomly selected sample, it said 60%, but it's only 400 people. Can we say based on that 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 she would have more than 50% of the vote. Different is it different than 50%? Let's try that. Let's see. What are we saying here? What's our null hypothesis? Right? Our null hypothesis is that she doesn't have more than 50%. P cap is, I'm going to say, is equal to, you could also say equal to or less than, right? P0, I'll call it, okay, for everybody, right? That's my null hypothesis. What's my alternative hypothesis? My alternative hypothesis is that P cap for Christine Quinn is different or greater than P0. I'm going to do it two-sided, only because it's going to be simpler for us. If you sit down and really think about it, you could actually do this twice. Do it the first time one-sided, two-sided, and then go back and actually reason it out, because really what we're interested in is a one-sided test here, right? Because we're only interested in this question is if she's more. But let's, for everybody, we want to do it two-sided to start off with, just to make it more rigorous, okay? But if you want, you can go back and do it again two-sided. I'm going to do it one-sided. It's equal or it's not equal to 50%. Does she have a different number than 50%, more than 50% being one of the options? Okay, so how am I going to test this? I need to know what my z-score is, what my z-score or my t-score is. Well, it's always going to be a z-score with proportions, because you always need to know that, well, in one group you had 230, in the other group you had 170, right? So you had more than 15 in each group, so it's more than 30, so you can use the z-score. So it's always, for proportions, you can forget about the t-score, right? So the z-score is going to be equal to, z-score is going to be equal to p cap minus p0 over the standard error. Okay, so now what's that equal to? P cap minus p0 is 60% minus 50%. We're testing it against the probability that she has just barely 50%. She doesn't actually have 50%. Okay, that's going to be equal to 0.10. Okay, over, what's the standard error? How do we calculate standard error here? Anybody remember? Standard error is equal to P times 1 minus P. Help me out here. I'm tired too. Okay, over N, we take the square root of the whole thing. Look familiar? You've seen that before, right? Okay, humor me. Okay, so that's the square root of, what's that? Okay, well, you want to know something? That could be Christine Quinn, or it could be the 50% for the other group, that 50%. I'm going to use 50%. Why? Because that's what we're comparing it to, and we're comparing it to what the real population is. We're concerned whether the real population, she would have more than 50% of the vote, but also because that's more conservative, because that's the biggest number we can get is 50%. So I'm going to call that 0.50 instead of 0.60, and this is 0.50, right? So that turns out to be 0.25, right? Over, what was it? Sample size, 400. Okay. So 0.25 divided by 400, take the square root of that. Point 0.25, oops, clear, 0.25 divided by 400 equals, I got 0.000625, and I'm going to take the square root of that. I get 0.025. That is equal to 0.025, 2.5%, 0.025. Okay, so 0.025 is my standard error. So I got 0.025, 0.025, 0.025 into 0.10 is equal to 4. So Z is equal to 4. Is that bigger than 1.96? Does Christine Quinn, can we reject the null hypothesis that Christine Quinn doesn't have 50% of the vote and say that we're 95% certain that she does and she wins the election? Yes? Okay, so you get the idea here. You're using the same mechanics that you use to calculate confidence intervals now in a different way. Now you're determining from the difference between a population mean and a sample mean, or later on we're actually going to work with two samples. We're going to work with something called a t-test, right? Probably next week, next session, we're going to work with something called a t-test, where we're not going to have two populations. We're going to compare two groups and not know either one of them's population's mean or standard deviation. We'll only have information about the samples for those two groups, right? So we'll actually compare two samples to each other, not a sample to a set value like 50%, or a sample to a proposed mean for an entire population like we've been playing with today to make things a little simpler. We're actually going to, and we're going to use a very similar formula. Again, it's going to be difference between the two means over some measure of the spread, the standard deviation. Yes?
So does that mean she wins the election or she doesn't win?
This means that she has more than 50, where there's less than 5% chance that she doesn't have more than 5, that she has the same as 50% or less. Okay. So there's less than 5% chance of that happening, which means that most likely she does have more. Right, so we can reject the null hypothesis that she has 50% and accept the null hypothesis that she has different or more than 50% in the real entire population. Right, so we're saying she wins the election, basically. Right, are we sure she wins the election? No, we're not. We're 95% sure, or there's 5% chance of us being wrong. And if you look carefully, what did we say here? When we did a confidence interval, we used 2 standard deviations times, let's say, standard error times 0.025, 2 times that would be 5%. What is that 5% called that we added and subtracted to the what we thought the proportion was? It's called the margin of error, right? That margin of error, that amount that you add, in other words, when they have a presidential election, Barack Obama, we predict he has 49% of the vote, plus or minus a margin of error of 3%. Z-score times the standard error is what that margin of error was, right? They calculate it the same way as we do. Okie doke. Good night, guys. Session 1, so I uploaded it while we were out before. It's probably being processed on YouTube already. I'll post a link to it so you can go back over this in their session and they can look at your session. Hopefully this comes out and I can get it uploaded tonight and stuff like that. Okay, and have a great spring break, okay? Hopefully the weather will be a little bit better for you next week. Okay. And like I said, the sessions in between are voluntary.